Have you ever just stopped and wondered how all your devices, your phone, your laptop, your smart speaker, all manage to talk to each other through thin air? Well, today we're pulling back the curtain on the magic of wireless communication. We're going to explore how simple data becomes an invisible signal and, crucially, how our incredibly crowded networks avoid collapsing into total chaos. Right, let's just dive in with the question that gets to the heart of it all. How in the world do all of these different gadgets use the exact same Wi-Fi network without creating a constant, massive digital traffic jam? Answering that one question is pretty much our entire mission here. It all starts with a really fundamental translation. Your data, the video you're watching, that text you just sent, the song you're streaming, it can't just fly. It has to be converted into a physical signal, an actual electromagnetic wave that can travel across a room. And this happens millions and millions of times every single second. Now, the most basic building block for that signal is the simple sine wave. And we can describe this wave with just three key properties. Its amplitude, which is basically its strength, its frequency, or how fast it's wiggling back and forth, and its phase, which is its starting point in time. These three characteristics are the knobs we can turn to encode all of our data. And that process of turning those knobs, that's called modulation. It's this absolutely ingenious solution for getting our digital ones and zeros onto an analog radio wave. We take a nice, steady, predictable carrier wave, and we literally alter its shape. We modify its amplitude, or its frequency, or its phase to represent our digital information. So there are three basic ways we do this. With amplitude shift keying, or ASK, a strong signal could be a 1 and a weak signal could be a 0. Simple enough. With FSK, maybe a higher frequency is a 1 and a lower one is a 0. And with PSK, we shift the very starting point of the wave itself. Each one of these methods is kind of like a different dialect for speaking on the airwaves. But here's a thought. Why turn just one knob when you can turn two at the same time? Well, that's the whole idea behind quadrature amplitude modulation, or QAM. It cleverly combines changes in both amplitude and phase simultaneously. This lets us pack so much more data into every single signal, which is exactly why it's the dominant method for high-speed Wi-Fi and our cellular networks today. So great, we've figured out how to encode our data and send one signal. But our original question was about preventing chaos when everybody wants to talk at once. How do we manage that mess? The answer is a technique called multiplexing. If wireless communication is our invisible highway, then multiplexing is the process of painting the lanes on the road. It's a whole set of techniques that lets multiple signals travel over that same link at the same time without, crashing into each other. So one way to do this is with frequency division multiplexing, or FDM. Basically, every device gets its own unique frequency channel, its own private lane on the highway. And to make sure nobody drifts and causes a pileup, we separate these lanes with unused frequencies we call guard bands. They're literally the empty buffer space, just like on a real highway, keeping everyone safely in their own lane. Okay, another approach is to share by taking turns, sharing time instead of frequency. The old way, synchronous TDM, gave every single device a reserved turn to talk. The problem, though? If it's your turn but you have nothing to say, that time slot is totally wasted. It's like a city bus running with reserved seats that are always empty. Statistical TDM is so much smarter. It knows internet traffic comes in bursts, so it gives out time slots on demand, only to the devices that are actually ready to send something. It's like a super efficient shuttle service that only runs when a passenger is actually waiting. So this brings us to a really crucial distinction. Multiplexing is the physical engineering of the highway, how we combine the signals onto one link. Multiple access, on the other hand, is the set of traffic rules that decides who gets to use that highway and when. You can think of it as physics versus policy. Okay, that's enough theory for now. Let's make this real. How does your Wi-Fi router at home use all of these concepts to prevent total pandemonium every single day? Your Wi-Fi network uses a set of traffic rules called CSMA/CA. Now, that name is a total mouthful, but the concept behind it is beautifully simple and honestly kind of polite. Listen before you talk. Before any device even thinks about sending data, it first listens to the airwaves to see if the coast is clear. And the process is just wonderfully polite. So a device listens, if the channel is free, It doesn't just jump right in. No, it waits for a tiny, specific amount of time, it's called an interframe space, just to be double sure nobody else is about to start talking. If the channel is still quiet after that little pause, then it transmits. It's the digital equivalent of not interrupting someone. But politeness only gets you so far. This brings us to what's called the hidden station problem. Just imagine two people are in separate rooms, so they can't hear each other, but they're both trying to talk to a person standing in the hallway between them. They're just going to talk right over each other, creating a garbled miss. Well, that's a huge issue for wireless networks. So, what's the solution? Well, it's a clever reservation system. Instead of just starting to speak, devices can first ask for permission, which makes sure that everyone else in the area knows to stay quiet for a moment. And this whole reservation happens with a quick two-part handshake. Your laptop sends a tiny little request to send message to the router. The router then broadcasts a loud, clear to send message to everyone in its range. That CTS message is basically a universal do not disturb sign, telling every other device, even the hitting ones, hey, wait your turn. Now the original laptop can send its data completely collision-free. Pretty smart, right? So when you take a step back and look at the whole picture, you see this amazing ladder of solutions. We start with the simple physics of a sine wave. We build on top of that with modulation to encode our data. Then we add multiplexing to create lanes on our highway. And finally, we layer on smart access rules like CSMA/CA and that RTS/CTS handshake to direct all the traffic. Each step is just an elegant answer to the problem that came before it. So that brings us to today. We've built this incredible system, but our invisible highway is getting more crowded every single day with billions of new smart devices coming online. So the real question is, what new rules of the road will we need to invent to prevent a global traffic jam? Something to think about. Thanks for tuning in.